All right. So today, for the first Quiver meeting of 2025, we have Hao Zhang, who will tell us about atomic Higgsings of 60 SCFTs. Take it away.
Okay, thank you very much. I'm Julius. So thank you for having me for the first Quiver meeting in 2025. It's my great pleasure. And also thanks everyone for accommodating my time zone request. Okay, so today I'm going to talk about atomic Higgsings of 60 superconformal field theories. It'll be based on two papers I had with a fellow postdoc, Jiakang Bao, also at Calgary IPMU. And the first one came out last September, and the second one came out earlier this month. So the plan is to first give some background of the F-theory tensor branch description of 60 superconformal field theories, which will be used heavily in our classification of minimal Higgsings of 60 SCFTs. So the way we call it atomic is because it actually means minimal Higgsing, but the word minimal also appears in many other contexts like minimal nilpotent orbits, for example. So we want to change another name. So we chose this name atomic that mimics one of a more famous paper. Okay, so backgrounds. Why are we
just because you mentioned the language, and sorry to ask a question so early, but so the atomic here does not refer to the atomic classification, right? Because so Higgsing an atom could have many steps, right? Am I right about this? Or
yeah, good question. It's not exactly.
If you take a 60, yeah.
Yeah. So it's not the decomposition of tensor branch into constituents, but it shares the idea of reductionism. So I want to break a Higgsing down to minimal possible steps, right?
But I mean that is if you have a rank 1 theory, so this we could then refer to as an atom. This could have like the many atomic Higgsings inside of this atom. Like it will not be a single step, right?
That's true. Yeah.
And maybe it's not. Okay, good. Yeah, just to clarify because there are two atoms. Good. Thank you.
Yeah,
please continue.
That's the question. Yeah. Okay. So, why are we interested in 60 superconformal field theories? So conformal field theories are fixed point of renormalization group flows, and for people who want to study them with more structure, it would be like oftentimes people consider conformal field theories combined with supersymmetry. And by doing so, the largest dimensionality that allows for superconformal algebra was determined by Nam in 1978 to be fixed space-time dimensionality. But the construction of non-trivial, so 6 dimension is also sufficiently high so that a 2-form field, which is coupled to a string state, cannot be dualized into lower form fields. Like for example, in 5D, you can dualize a 2-form continuous field into a magnetic dual 1-form field. So we say that in 60 theories, there are effective strings that are tensionless. And moreover, interacting 60 superconformal field theories are only known to be constructed by string theory. Sorry for the typo. Right, so the first construction was the construction by Seiberg in 1995, where 60 SCFT was identified as world volume theory on NS5 branes. I missed, but it has to be in type 2A string theory that are and the NS5 are magnetic dual to the fundamental strings. So in some sense, it is the world volume theory of some fairly fundamental object. And as many people know, we can further compactify the 60 superconformal field theory to generate strongly coupled QFTs in lower dimensions. And this explains why it's interesting. Okay, so then why are we interested in RG flows among 60 superconformal field theories? So here, more specifically, we mean that we first turn on a VEV of a scalar or some linear combination of scalars, either for scalars all in the tensor multiplet or for scalars all in the hypermultiplet, and then flow to the IR. But sometimes we still use the term RG flow to refer to the whole process. And so basically it tells us how the superconformal field theories are related to each other. And it is usually hopeless to obtain explicit and exhaustive knowledge or somewhat exhaustive knowledge for RG flows in whichever dimensions, even if 8 supercharges. Or to try to tackle this question, it would be quite natural to start from the dimensionality where there's most constraints, which is exactly in 6 dimensions. So for 61,0, with the help of F-theory classification, it is relatively more tractable to get such a knowledge. And in addition, these RG flows give intricate moduli space geometry. So especially there's a hierarchy of symplectic singularities via the Higgs branch. And in some sense, it is by examining all the flows among these 61,0 classified by F-theory, we can also try to validate or to probe the completeness of the F-theory classification. Like, is there a case where in a theory a theory constructed in F-theory flows to another theory whose F-theory construction is not known? So we wouldn't be saying anything about this question, but it would be a long-term perspective or long-term motivation to keep in mind of why this is interesting. Okay, now let's come to more concrete field content in 61,0. So the 60 spinors are subject to pseudo-Majorana Weyl conditions, which means the left-handed or right-handed are independent. So there's 2 count of supercharges, and each supercharge has 8 components. So the 61,0 supermultiplets would so first, there's 2 familiar types, which is hypermultiplet, which contains 2 fermions and 4 scalars. And then there's vector multiplet, where we have a vector and 2 fermions. So there's no scalars in the vector multiplet for 61,0. But then there's the field unique to 60, which is the tensor multiplet, which has a 2-index tensor plus 2 fermions plus a scalar. So basically the moduli space. So there's 2 branches of moduli space of vacua, the tensor branch, which gives vectors to scalars in the tensor multiplet, and Higgs branch, which gives vectors to scalars in the hypermultiplet. So in the F-theory construction, we'll see that if we just care about the connection, the flows among different SCFTs, then determining the tensor branch is simple in a sense that you can just take a curve and decompactify it. And that is, or like, in other words, the BEV of curves on the tensor branch are explicitly controlled by volumes of the curves. But on the other hand, the Higgs branch is way more challenging than this. So it would be the main challenge that we will try to pursue today using the F-theory construction. So the strategy is that given a 60 SCFT, we try to find all the atomic Higgsings, and then we iterate this procedure to generate the entire Higgs branch Hasse diagram. But okay, so now we need more background, which is some motivations for the F-theory classification. So as we mentioned, the 62,0 was first identified as the IR limit of the world volume theory in type 2A. So soon it was realized that if you use type 2B, then you can get an ADE family of 62,0 theory, which is identified by Witten to be type 2B string theory on C squared gamma AD, so Kleining singularity. And this in fact exhausts all possibilities of 62,0 SCFTs. And one can slightly combine these setups to generate some 1,0 theories, like you put like either one of type 2B string theory on a Kleining singularity, and you also put an S5 on this singularity. This way you get some specific 1,0 theories. Or another possibility is that you take M theory and you put an M5 brane on top of this transverse C2 mod gamma ADE, and you put the whole thing into an M9 wall. This will give you Orbi instanton theories that will be kind of special toward the end of our talk. But on top of these, there's a much more broad family of classification of 60 superconformal field theories using the language of F theory. It was done by Heckman, Morrison, Vafa, and Rudelius in these two papers in 2013 and 2015. So it not only incorporates all the earlier cases, but also provides many new cases. And there's, as far as I know, there's no convincing outlier so far. And therefore, we analyze the RG flows using the F theory, the Higgs branch, Higgsings using the F theory tensor branch description. Okay, so F theory describes a non-perturbative regime of type 2b. And this means in type 2b, there's, in the strongly coupled regime, there's the two-form potential C2 and B2, which transforms into each other. And the F theory wants to introduce a T2 vibration, a two-torus vibration over the 10-dimensional space-time, so that the SL2Z large transformation of the F theory torus geometrizes the gauge symmetry on this, geometrizes the large gauge symmetry on C2, B2. And in particular, the gauge group is given by the loci where this T2 vibration becomes singular. So the singularity of two torus is classified by Kodaira. And from that you can read off the gauge symmetry that you have in the infrared. Okay, so based on F theory, 61,0 superconformal field theories are engineered by considering a non-supersymmetric orbifold, which is C2 mod gamma U2, where the fact that gamma U2 is a subgroup of U2, but not SU2, would break supersymmetry if you were just to do type 2. But now you can further decorate the space with a non-trivial two-torus vibration to restore supersymmetry, as long as the entire vibration becomes a Calabi-Yau threefold, an elliptically fibered Calabi-Yau threefold. So then the singularity by itself is hard to analyze, but by blowing up the curves, by blowing up the singularity, by resolving the singularity, you go to the tensor branch, which is more tractable to analyze. So as an example, to illustrate the idea of resolution, I would just consider a 2,0 theory by applying a singularity of C2 mod, let's say gamma E6, where gamma E6 is the binary tetrahedral group, which is Mackay dual to the Lie group E6. And you resolve the singularity, and mathematicians told us that we should get a collection of 6 CP1s, which intersect into the negative of the Cartan matrix of E6, which means each complex curve has self-intersection -2, but pairs of adjacent curves on this graph have mutual intersection 1. So like when I started, the notion of self-intersection was also a tricky information. So mathematically it encodes some property of the normal bundle, but like intuitively one can think of it as some rigidity that doesn't allow you to deform the curve or so. So these notions have physical consequences in 6D, because if you wrap D3 brane on these CP1s in the internal manifold, then CP1 has 3 + 1 dimension, and then you will end up with 1 + 1 dimension in 6D. So these will be the effective strings that you get in the 6D space-time. And the direct pairing of the effective strings will be encoded by this geometric intersection pairing. Right, so Aij intersection, which is a geometric quantity, translates into the Aij Dirac, which is a physical quantity in 6D. Okay, so now remember what we did is that we took a special singularity and we resolved it into a collection of curves. Now we sort of want to think in the other direction, which is if we take another random configuration of curve, how do we know that it can be obtained from resolving a singularity? Or how do we know that we can simultaneously contract all of them down to a singularity? So this was answered again by mathematicians like Mumford and Artin in the 1960s, that the simultaneous contractibility requires the intersection pairing matrix Aij to be negative definite. Right. So in particular, the diagonal term needs to be negative, which means the self-intersection of each curve is always less than 0. And as part of the jargon, which some of you might have seen, a CP1 with self-intersection minus n will be denoted simply as the number n. Like, the idea is, for those who worked on it a lot, every curve have self-intersection, so we might drop the minus sign. And later we'll see that the structure that the fiber singularity stays within the Kodaira type requires n to be an integer between 1 and 12. Okay, so for example, if I draw the number 2 twice next to each other, it means I'm having two CP1s that's like intersecting each other, and each has self-intersection minus 2. So as we explained, it will give a 62,0 theory of type A2. So one can get it from type 2b on C3 on C squared mod C3 or 3 NS5 branes in type 2a. Okay, so now we can decorate it with fiber singularities. So now in the second theory, where on top of the A2 2,0 theory, I write an SU4 Lie algebra on top of each of them. It means that, like in the geometry, we decorate each curve with an I4 type Kodaira singularity. So you imagine there a torus has 4 pinch points. So it becomes a shape of 4 sausage that connects into a circle. And this shape will give you SU4 gauge group, because you can, like by FM theory duality, you can wrap an M2 brane on one of the sausages to get the cartons in the FN SU4. Okay, so by having 2 gauge, right, and in the 60 physics, the SU4 gauge theory is in a sense paired with this tensor, which physically means that the gauge coupling of the SU4 gauge group is inversely proportional to the square of the volume of the tensor. So like when you take the limit of the whole configuration shrinks to a singularity, the gauge coupling becomes infinite, and you get a strongly coupled superconformal field theory. And by having 2 gauge symmetries adjacent to each other, the notation implicitly means that there is a bifundamental matter at the 4 bar representation. So the fundamental of one SU4 times the anti-fundamental of another SU4. So up till now, I've just been talking about gauge symmetries, but it will be an important physical remark that only flavor symmetry would be meaningful at the SCFT point, but the gauge symmetry will have infinite coupling and becomes meaningless. So in the above configuration, there is a flavor symmetry there's a non-abelian flavor symmetry that is SU4 times SU4, and each.
I have a question. Maybe I didn't quite understand the comment about the just flavor symmetry is meaningful, but for example, if you look at this equation at the bottom, I could add more gauge nodes to this, and the flavor symmetry could be the same, right? Like there's some more information than just this. I mean, of course, at infinite coupling, it will be distinguished, but
yes.
How do you
thank you for the clarifying question. I was not trying to say that flavor symmetry is the only data.
Okay, understood.
Yeah. So I was only trying to say that gauge symmetry is something that's not actually accessible at the SCFT point. Flavor symmetry is something that is accessible.
Of course, also the baryonic symmetry, so you can still distinguish, but there are extra you want here, but again, good. Okay.
Right. Yeah, so it'll be on the last line, right? So there's also a delocalized U1 flavor symmetry that's shared among all the curves. For example, that was discussed in like from the F-theory perspective in a paper I had with Abruzzi, Fazzi, Heckman, and Rodelius. So the full flavor symmetry is SU4 times SU4 times U1 if you forget about discrete quotients. Okay. So so basically the 60 tensor branch description is very rigid in the sense that if you take a curve, you specify the self-intersection and the gauge symmetry, then it almost always fixes the matter content and the total flavor symmetry. There's, I think, one or maybe at most a few exceptions, but they won't show up in examples of this talk. So, and the anomaly cancellation, so this, the fact that the matter content is fixed by the anomaly cancellation is nice, but sometimes the anomaly cancellation wants to spit out a negative number of flavor symmetry. But like physically, we only want to consider non-negative flavor ranks. Therefore, that would in turn impose some constraint on the pair of self-intersection and the gauge algebra. For example, if you have a curve with self-intersection -3, then the gauge group the gauge algebra must contain SU3 as a subalgebra. And also, if you have self-intersection -4, then the gauge must contain SO8. And like if you have multiple curves touching each other, then the practical procedure is to first take a maximal flavor symmetry, for example, for the second curve as F2, and then think of the gauge of the first curve G1 as a subalgebra of F2 that was gauged, and only the remnant, the commutant symmetry of F2 inside F2 with G1 will remain as the flavor symmetry of the second curve. And speaking about the non-negativity of the flavor rank, it's natural to talk about the non-Higgsable cluster. So a curve with self-intersection -2 can be Higgs down to like all the way down to the 2,0 theory. So all the gauge group can be Higgsed away. But this is not true for a curve with higher self-intersections, like a -4 curve can, like when the gauge is already SO8, then you can no longer Higgs it at all. And therefore, this single curve configuration is called a non-Higgsable cluster. And in fact, all the non-Higgsable clusters has been constructed by F-theory, has been classified by this F-theory tensor branch. So there are a few single curve NHCs and also 3 multi-curve NHCs. Okay, so these non-Higgsable clusters will show up as part of the theories where we have basically used up all possibilities of non-abelian Higgsings, but we need to look for other type of Higgsings. We'll see them later. Okay, so there is, we're almost at the end of the background where let me introduce a family of popular 60 superconformal field theories called conformal matter theories. They're nice because they also admit a simple M theory description as a stack of M5 brane on a C2 mod gamma singularity. And it is called G, when the singularity is Mackay dual to G gauge algebra, then the theory you get is called G, G conformal matter of rank K. So to explain the jargon, let's try to write down a candidate tensor branch description. So we would hope to just take the 2S. So let's take G equals to SO8, and we want 3 M5 branes. So it's very close to the 2SU4 example, but I want to change all the gauge and flavor to SO8. So now I want to naively write it like this. But it turns out that this is problematic because at the complex codimension 2 intersection, the presence of a pair of SO8 would make the fiber too singular. So it will be brought above the Kodaira classification. It will be a non-minimal singularity. Therefore, the solution to this situation is to blow up the base to introduce new exceptional divisors. And in particular, you need to do this with each pair of SO8 intersection, both gauge and gauge flavor. So you introduce 3 exceptional divisors, which also changes the self-intersection of adjacent curves. So in the end, you get this pair of 14141 configuration with -4 curves supporting SO8. Therefore, the overly singular SO8 pair intersection is well separated, and you've finally gone on to the full tensor branch. And this is called conformal matter. And like, if you then look at what shows up at the intersection, then you get an E string. And the E string is called D4 conformal matter of rank 0 because it is analogous to the bifundamental 4 bar, but now it is a strongly coupled SCFT itself. So you increase the number of M5 grain to get higher rank conformal matters. Okay, so for example, we like close to the end, we'll show you the complete Hasse diagram of conformal matter theories for any G and K. Like we'll describe a method of how to compute them, and we'll give a gallery of a few examples. But the rest of the talk will be dedicated to the explanation of how our algorithm works in producing such Higgs branch Hasse diagram. Okay, so on the name again, the atomic classification paper back in 2015 was to analyze all possible tensor branch configurations of SCFTs down to these non-Higgsable clusters and connected by conformal matter theories. So using the atomic classification, we have a collection of F-theory description of 60 SCFTs, and we can write down some examples of Higgsings. And for example, we can reduce the gauge rank from SU5 to SU3, for example, but of course, I'm deliberately choosing one that's not atomic, not the minimal step for the moment. And the second example would be to blow down a -1 curve. It may or may not have a flavor. It may or may not have a gauge symmetry. And there's also a nilpotent Higgsing, which is associated with a VEV inside of a flavor symmetry that is nilpotent. So it is parameterized by a nilpotent orbit inside a flavor symmetry, and it may or may not be the largest, or you may or may not choose the largest, the smallest nilpotent orbit. So if you choose a large nilpotent VEV, then it could have a dramatic effect on the tensor branch. As you can see, it blows down multiple -1 curves, and there's also various Higgsings going on. But as I said, I purposely choose 3 examples of Higgsings that's not the smallest possible steps. So in the idea of atomic Higgsing, as nicely clarified by Julius, the word atomic should just be understood as the idea of reductionism. So we try to break down all the Higgsings we try to break all Higgsings down to the minimal possible steps. And then we iterate to get the entire Higgs branch. So in our first paper, we outlined the procedure to identify all atomic Higgsings, and they basically organize into a few types. The first one is a Higgsing by a minimal nilpotent VEV of a non-abelian flavor symmetry. And the second one is an atomic plateau Higgsing on the gauge group. So we basically counting the gauge rank, and there will be some curves where a collection of adjacent curves where the gauge ranks are the same, and that sort of forms a plateau, and we need to decrease that collection of gauge rank. And the third possibility is atomic combo Higgsing, which importantly involves a combination of blow down and Higgsing of gauge symmetry, but that is surprisingly the minimal step. And there's a fourth type, which is atomic Higgsing into multiple component, which we can sometimes call endpoint changing Higgsing. So this type of Higgsing is mysterious in that we don't know how to analyze them in the F-theory description, but that would eventually bring us to the second paper where we have something to say for this type of Higgsings using M-theory. And as a disclaimer, these types are not mutually exclusive. So for example, a minimal nilpotent Vev of an interestingly placed flavor symmetry can actually trigger a combo Higgsing at some point. And in our first paper, we understood the first two types of Higgsings in general and the last two types of Higgsings in many examples. And in our second part, we took all the theories that has nice M-theory constructions, like conformal matter theories and or Bien-Tantan theories. And for these theories, we have a systematic understanding of the last three types of Higgsings. So I should be honest that this whole research is crucially inspired by the magnetic quiver study. So both the quiver subtraction and decay and fission. So very clean and explicit Hasse diagram were obtained for theories where there are magnetic quiver constructions. So we try to. So what we did at an early phase is to translate these rules to the tensor branch and see that there are clearly patterns that generalizes even to cases that we don't yet know the existence of a magnetic quiver. Okay, so let's start at the first case, the atomic Higgsing by a nilpotent Vev. So why nilpotent? Because the semi-simple will essentially be the next case. So a nilpotent element inside the Lie algebra is defined by considering its adjoint action onto itself. So basically, you want to consider whether the action of an element to x times that element times x inverse as a map is a nilpotent map. For example, in this Lie algebra SU2, it's easy to write down a nilpotent element which is 0, 1, 0, 0, because you can take powers of it and it eventually becomes 0. And they form orbits under complex conjugation. And different orbits, as we know for any equivalence class, are disjoint from each other, but mathematicians still came up with ways to compare them by considering the closure ordering. So we say OX is less than OY if OX is contained in the closure of OY. So you should imagine that the larger orbit have some exclude some higher codimensional regions, and the closure would fill in the higher codimension regions which contains the smaller orbits. Okay, so a minimal nilpotent Vev in a non-abelian flavor symmetry is parameterized by the minimal nilpotent orbits, and fortunately there is always one, as proven by the mathematicians. And on the tensor branch, it oftentimes only affects the closest tensor that's attached to by this flavor symmetry. So for example, you can have a case where the flavor symmetry G is carried by a curve that has a gauge symmetry. I should actually call it script H. So then a minimal Vev of G will have the effect of a minimal Higgsing of the gauge symmetry, small g. And another possibility is when this flavor big G is touching a -1 curve without a gauge symmetry. And in this case, a minimal nilpotent Vev of this flavor symmetry G would blow down this -1 curve so that the next to adjacent curve will have self-intersection change to n-1, and you oftentimes, and like in general, get new flavor symmetry G prime. And as I said, there could be a combo Higgsing which requires both blow down of -1 curve and Higgsing of both script G and both frac G and frac H. So this will be discussed later. So we observe that it is true that the transverse slice is always given by by the minimal nilpotent orbit of the Lie group of the Lie algebra G. So like in the magnetic quivers, this is well known to be true. But for us, for theories with F-theory tensor branch, we can also check that the dimension change also equals to the quaternionic dimension of the minimal nilpotent orbit, which is given by the dual Cox-Sixter number of G. So for example, if we start from the D4 conformal matter and we try to just Higgs on one side, then the first minimal nilpotent orbit will blow down the -1 curve, so you get a -3 curve, and then you get an SP1 cubed flavor symmetry. You take one of them, and SP1 equals to SU2, and you turn on a minimal nilpotent orbit, which then Higgses the SO8 gauge down to SO7. And the next step is to Higgs this SO7 down to G2. So in all the cases we observe, the non-abelian flavor symmetries nicely corresponds to possible Higgsings. And yeah, so in comparison with this nilpotent hierarchy paper, this way we'll make sure that we are always looking for the finest possible Higgsings. Okay, and then we come to the atomic plateau Higgsing. So we try to examine the cases. There are also cases when we run out of non-abelian flavor symmetries. For example, here is a theory, but since this theory is a product of like sits in the IR of some conformal matter theory, we clearly expect this theory to be eventually Higgsable to a 2,0 theory. And to check that it does not have non-abelian flavor symmetry, we can use the formula of flavors to see that each curve, like only this curve and this curve at both ends of the plateau have one flavor and the other have no flavor. So we still expect this theory to be eventually Higgsable to 2,0. And in this case, we need to make use of the U1 flavor symmetry that's shared among the three SU4 gauge, the three curves in the middle with SU4 gauge symmetry. And then the plateau goes down from SU4 to SU3. So as I just said, this Higgsing can be viewed as given by the Vev of the delocalized or the baryonic U1 flavor symmetry that was identified to be delocalized in this paper 5 years ago. Okay, so you might wonder why can
this is still a nilpotent orbit type Higgsing, right? Like the slice involved. Is the slice here a nilpotent orbit or is it something else?
Let's see.
Or you know, something in the null cone. Like the geometry of the transition in the Higgs branch, is what I mean.
So this case, if you look at the magnetic quiver, then it is I think it's the node on the top.
We can also discuss later, like
Yeah. Okay, cool. So you might wonder why can I not just Higgs a single SU4 gauge symmetry? But then if I do that, but keep some other SU4s, I would give negative flavor ranks, which is not allowed. Therefore, like even if you want to just consider the consistency of flavor rank, you see that all the SU4s must be Higgs simultaneously, and in fact, that's the only possibility here. Yeah, so a general answer to Julius's question would be that we don't have independent ways to compute the symplectic slices except for this sentence where for minimal nilpotent orbits, we see that the slice is also given by the minimal nilpotent orbits. For the other cases, the best we can do would be to either see the dimension in which we know that this is 1, and then we can only, like when there is a magnetic quiver available, we need to rely on that. But of course, we hope to do better in the future with independent approaches. Okay, and now let's come to the third type, which we call combo Higgsing. So let's take a theory as I wrote here. So this theory is interesting in that there's 2 minus 1 curves, that's E strings, but other than these, the remaining 3 curves are all non-Higgsable clusters. So there's no non-abelian flavor symmetries. And you might say that the Higgsing has to do with the VAVs of the U1s, which I think is morally true. But let me tell you how I'm trying to analyze the product of the tensor branch. So to see that, so first of all, let me just tell you, without giving more detail, that this theory is somewhere in the IR of the D4 conformal matter theory. So you take that theory and you turn on some large nilpotent orbit of SO8, or you can also track little by little to reach here, where you notice that there's no VAV of non-abelian flavor symmetry to use. But then you also expect that it should eventually be Higgsable to a 2,0 theory. So, right, as I said, there's like the -3 and -4 curves are all non-Higgsable. But at the same time, if you want to just blow down the -1 curves, but don't do Higgsing on the gauge algebra, you would also get issues because like even if this -3 curve turns into a -2 curve, it's supporting a SU3 symmetry will only allow for a maximal flavor symmetry of SU6, which cannot touch a curve with gauge SO8. Therefore, one way to Higgs this is to reduce the gauge symmetry of this SO8, and one possibility is to make it down to SU4, but you also do the 2 Higgsings do the 2 blowdowns of the -1 curves simultaneously. So together, the result you get is a chain of 3 -2 curves, and the gauge is SU3, SU4, SU3. And the gauge reduction and the blowdown forms a combo, but you can compute the difference in quaternionic dimension, and you get that the difference is 1. So this is really the minimal possible Higgsing. So this is just like in the games where you need to press a combination of buttons so that you do a special move in these Street Fighter games. So that's why it's called combo Higgsing. And the delta quaternionic dimension is 1, so we know it's atomic. But we'll come back to this theory. We'll come back to this particular example later, where we see this Higgsing from a slightly different, from an alternative perspective. Okay, so right. In some sense, one can think of this as a DE type analog of atomic plateau Higgsing. I see something in the chat. Oh, okay. Yeah, no problem. See you. Okay. Yeah, so there's the case of atomic Higgsing into multiple components. So let's first do the simplest case of 2,0, where you have 4 -2 curves, which you can think of as a stack of 5M5 branes. And you split it into a stack of 2 M5 brane and another stack of 3 M5 brane. So then you get this Higgsing of 4 M5 into a theory of, sorry, you take the theory with 4 -2 curve and you Higgs it into the disjoint union of a theory with 1 -2 curve plus another with 2 -2 curves. And this is all nice and simple. And in 1,0 theory, we want to claim that as long as the 1,0 theory has a nice M theory construction, we can make nice predictions of what is the possible atomic Higgsings, even though we split into a disjoint union of multiple theories. So let's take conformal matter theories of M5, put on C2 mod gamma. And so the idea is that in addition to separating these M5s So yeah, in addition to separating these M5s, one also has the possibility to performing complex structure deformation on the C2 mod gamma so that it can be decomposed into smaller singularities. So let's take the C2 mod Zn case, which can be done explicitly. So the hypersurface equation of, for example, an I7 type singularity can be written as xy equals to z minus z0 to the 7th power. So it parameterizes the elliptic curve, which has a I7 singularity. And you can just deform it by taking 4 copies of z0 to z1 and 3 copies of z0 to z2. And you will get a pair of singularities, one of type I4 and the other of type I3. And to try to keep the Higgsing minimal, you want to do this deformation such that this z equals to z1 singularity. So you do this deformation, but you also split the M5 branes as above. And you want one stack of M5 brane to be coincident with one outcoming singularity and the other stack of M5 with the other outcoming singularity, just like I show in this figure where the singularity is deformed and the M5 brane is split, but each matched to a resulting Kleinian singularity. Okay, so now you might want to write down a Higgsing, which is 4 minus 4 each with SU7 down to 1 minus 2 with SU4 and 2 minus 2 with each with SU3. This is a valid Higgsing, but this is not an atomic Higgsing. An intuitive answer of why this is not atomic is because we haven't tried to fix the IR theory, but Higgs the UV theory as much as we can. To see how to do this, we know that in order to get this same IR theory, we don't need to keep the UV SU7 theory unchanged. This is because the UV SU7 theory needs to eventually be split into one stack of SU4 and another stack of SU3. So now I'm writing the SU4 symmetries by red dots and the SU3 symmetries by black dots. So if you want, this is some dual type 2B description where the fiber is given by 7 branes, just ordinary D7. And given that the red dots and the black dots needs to be separated anyway, I could have the possibility in the UV to turn on vevs that already Higgs that are massive excitations connecting each red dot with a black dot. So these vevs will not destroy my IR theory because these pairs of dots of different color will be separated anyway. And the lines I draw might seem random, but in fact, there's a general mathematical description. And the description says that the nilpotent orbit of trivial orbit inside SU4 and SU3 induces the nilpotent orbit of 2 to the 2 cubed, comma 1 inside SU7. So the way you describe nilpotent elements in SU-Lie algebra by the partition is just you look at the side of the Jordan block, and a number 1 is just no Jordan block, and the number 2 gives you a Jordan block of 0, 1, 0, 0. That's the smallest non-trivial line. And a number 2 corresponds to a line here. And this induction applies to all Lie algebra. So all like simple Lie algebra. So more concretely, there's an algorithm for classical type Lie algebra, and there's some catalog produced by Spaltenstein for exceptional type Lie algebra. And if you turn on this vev onto both the left SU7 flavor symmetry and the right SU7 flavor symmetry, you get the outermost SU7 gauge will be Higgs down to SU4 gauge. And the resulting Higgsing turns out to be an atomic Higgsing with the quaternion, with the difference of quaternionic dimension being 1. So as I said, this Higgsing is quite mysterious on the F-theory tensor branch. By that I mean, if I randomly tweak the numbers, I have no good way to tell whether this Higgsing is is allowed or not, and whether it is atomic or not, unless I use this prescription of induced vevs. The fact that the difference of dimension in being 1 is just a necessary condition, or like it says that the vev, if the flow exists, then it must be atomic. But if I randomly tweak the numbers, I could get false positives by some flow that doesn't actually exist. So here I use this dual M theory picture to show that the flow exists. And I'm taking some example where trivial vev in the IR induces non-trivial vevs in the UV. Okay, so now with this understanding, we can.
I have yet another question. Sorry.
Please.
Here, do you do only a Higgs branch, or do you also a little bit go on the tensor branch to reach these Higgsings?
Exactly.
You go a little bit in the tensor branch as well.
Right. So as you see in this picture, the left
because
side
as a pure Higgs branch flow, I can't really see the decomposition. That's why I'm asking.
Right. So on the left-hand side, this is the Higgs branch flow I want to describe. They sit at the origin of the tensor branch. And I'm claiming that I have no way than going to the tensor branch and describe it by the tensor branch. Right.
No. So but even on the left, because the 2M5s, like if you deform your C2 mod gamma singularity, like then you still have your M5s somewhere on there, but they're not on top of each other. So if you separate the M5s, some of them going to one singularity, some of them going to another singularity, then it looks to me like it's a mixed branch.
That's true.
Right. Okay, good. That was my question. So you're in this atomic Higgsing thing. You are looking at Higgs and mixed branches and all. Okay,
that's true.
Good. Thank you.
So we use the tensor branch description, but as Yuli's nicely said, we're trying to describe the Higgsing. And there's actually one fine print. So I said moving M5s, but if you move these M5s along, so what I mean here, I draw a line by C2 mod gamma. So the geometry should be understood as R5, 1 times the real 4-dimensional Kleinian singularity time and perpendicular direction R perp that's transverse to everything. And if I were to separate M5s along this line, I get tensor branch flow because the separation of M5s along this line is dual to the vev of the tensor multiplet. Therefore, I need to, if I want Higgs branch flow, I need to move the M5 perpendicular to this R perp, but along the Kleinian singularities. So yeah, this I didn't depict well on the figure. I'm only saying in words. And please ask again if you're, in the end, if you're confused. Right. Okay. So with this understanding of induced flows, we can also go back to a previous example of combo flows and see that we can reproduce it. So the idea of induced flow doesn't necessarily need to flow to irreducible theory. It could flow to reducible theory. So you could not separate the stack of M5 and only do you also do the complex structure deformation of the Kleinian singularity in that you only produce one smaller Kleinian singularity. Okay, so to reproduce the combo flow we've just got, we notice that the IR theory can be obtained from a conformal matter, an A4 conformal matter, quote unquote, of rank 4 and the reduction from SU4 down to SU3 can be obtained from a vev 2, 1 squared. So that's the minimal nilpotent vev in SU2, in the would-be SU4 flavor. And then the UV theory of this combo flow can also be obtained from a vev of 3 squared, 1 squared. And that vev is a combination of multiple minimal Higgsings, which according to this nilpotent hierarchy paper will indeed produce a single-sided theory of where this 1 for SO8 is turned into 3 SU3. And you do this VEV in both cases, you get the UV theory of the combo flow. Now the key point is that if you take this SU4 theory, now the key point is that if you take this SU4 VEV of 2, 1 squared, and you ask what is the induced nilpotent orbit of that in SO8, you exactly get 3 squared, 1 squared, which now, as we've seen, reproduces this combo flow as an induced flow. So it's complicated to explain in real time what was the mathematical definition of induction, but for now, it's very helpful to know that for all the cases that we care about, the induced orbit it must exist and it's also unique. So, okay, right. So even for us, we first identified the existence of this combo flow, and after a few months, we realized that it can be thought of as an induced flow. So it was even amazing for us, not just for the purpose of presentation, for storytelling. Okay, so now as a showcase, we show some complete Hasse diagram for E, E type conformal matter theories. So we did the E6, E6 of rank 0, of rank 1, and E7, E7 of rank 0. So as some snapshots from our paper, they look like this, where the boxes just have some labels, and like in addition to these Hasse diagram, we have independent catalogs that writes down the tensor branch description for each node, and also which theory it flows to. Therefore, if we want to look at our data, then the catalogs are eventually more helpful. And the Hasse diagram is just to give you a rough idea. And now to compare with the existing literature, like including one I had with Hassler, Heckman, Rocher, Rudelius in 2019. Basically there, people always want to take the UV theory and turn on various nilpotent VEVs from the smallest all the way up to the largest. But now we only want to proceed by first turn on the minimal nilpotent VEV and get the new flavor symmetry, and turn on the minimal nilpotent VEV with the new flavor symmetry. In principle, we can get more cases. And in practice, for this simplest case, we didn't get new cases. But for both the middle chart and the right chart, we do get new cases. In particular, in this E7 nilpotent orbit, there is a way to Higgs that down to the, in the E7 minimal conformal matter, there is a way to Higgs it down to the E6 minimal conformal matter. And this was previously inaccessible in this approach. Okay, and we didn't try E8 because it's in principle the similar algorithm, but the diagram would be even more crazy than what we did here. We're a bit lazy here. And I think we're out of time, so let me try to spend maybe 1 minute to explain what I did for the rest of the slide. So the idea is that we can take conformal matter and put it inside another M9 brane to get Orbi instanton theory. So there are also some tensor branch description of gluing. And if you do this, then a boundary condition of a nilpotent orbit inside SU4 is changed into a flat E8 holonomy inside the asymptotic infinity of S3 mod Z4. So it is given by a discrete homomorphism from Z4 to E8. And basically the figure is mostly the same, except that you have M9 brane on one side. You could also have M9 brane on two sides, but I'm not gonna describe it in the talk. So the idea of induced flows is exactly the same, but the mathematical notion of induction for discrete homomorphism is not available in the literature. Therefore, we define it. And the way we define it is that like it's in two layers. So for A types, the homomorphism are classified by cut labels. And the way we define it is very algorithmic by saying that if we want to consider an induction, then we just take union of the cut label. And I could explain more if there's more time, but let me just say that it is an experimental result where the algorithmic understanding is like goes farther than the geometric or topological understanding, which we hope to have in the future. And we can have induced flows where it gives us it is given by a combination of induced nilpotent orbit and an induced discrete homomorphism, which we can write down explicitly in the A-type case. And for DE type case, there was not even classification. There was some case-by-case classification by Frey, which is too complicated, and we won't use that. And in Frey and Rudelius, they matched the DE type homomorphisms with 60 SCFTs as IR of the Orbi-Instanton theory. So in this sense, we can say that we can always identify the induced flows for the IR theory being one component. And in these theories, we can define an induction from A-type homomorphism to DE type as defined by the SCFT according to Frey and Rudelius. Okay, so conclusions. We outline a procedure to identify all atomic Higgsings of any given 60 SCFT based on their F-theory tensor branch description. So for some flow types, like the minimal nilpotent web and the plateau Higgsing, the flows are well understood in the F-theory description. But for other flow types, we can do examples in F-theory, I mean the combo flow. But they are better understood if there's a dual M-theory description, which I mean conformal matter theory and Orbi-Instanton theory. And for theories with unitary and orthosymplectic, for some unitary and orthosymplectic type theories where a magnetic quiver description is available, we, like our results, match the result for atomic Higgsing and the result from the quiver side. And in fact, that's a key source of inspiration for our project. And by match, let me emphasize again that we don't have an independent way to determine the transverse slice other than the minimal nilpotent web case. And future directions, so one is to, as I said, to identify the transverse symplectic slides based on the F-theory case, based on the F-theory, purely based on the F-theory description. And the second one is to see if it's possible to understand the flow into reducible theories only using the F-theory description, which is now completely unavailable. And a third direction is to try to study the 60 little string theories by understanding T-dual pairs of atomic Higgsings, which I noticed that Marcus and Lorenzo had some paper at the end of 2023. And something I didn't write down is that to look at flows which preserve some generalized global symmetries and track to see what are the implications of those generalized symmetries. We only have such examples, but we don't have any interesting thing to say of what does the generalized symmetries tells us yet. And we hope to look into that in the future. Okay, thank you very much for your attention, and questions are very welcome.
All right, well, let's thank Hao for this nice talk. Yes, do we have questions? So I already asked a bunch. Mario, you just unmuted. I will let other people go first.
Okay. Yes, can I ask you, hello, can I ask you, is my ignorance actually, but is there like a list of the minimal Higgsings in the magnetic quiver literature? And if yes, how dense is the set of minimal 6D Higgsings inside this set of minimal Higgsings?
I think many people in the audience knows it better than me. But for me, it's this Quiver subtraction or decay and fission, and yeah.
So the denseness question, but there is no classification, first of all, of possible isolated singularities. Then you can ask which one has, for example, a representation as a quiver. This is some subset, and there like Antoine, Marcus, Jiakang Bao, and others have thought about this with the decay and fission approach to ask a question of, take some unitary quiver. Is it going to be minimal slice? So you can kind of, for a given dimension, you can ask what are all of them.
Yeah.
And then the question in 60, how many appear? It's that sometimes you have infinite families where you have something like think of a discrete quotient. You can say something mod zk. And then some examples of them will appear in 60 theories, but not everything.
Not everything,
So
okay.
definitely not everything. So you could have C2n mod zk for any k, but most of this will not show up.
Okay.
Yeah, but then the k equals to 2 will show up and things like this. Yeah.
Okay, thank you to both of you.
So, just would you say that you see absolutely every leaf in the Higgs branch of a 60 SCFT? Like, are there leaves that you could be missing? Like, are there transitions that you could be missing?
Let's see.
Like, or if you compare to the literature, let's say, do you match all of this? Like,
Right.
okay.
Right.
Yeah. Okay, good.
So in practice, the combo flows is difficult to identify, and moreover, as I said, the flows into like irreducible theories. The flow into multiple irreducible components. We just don't know how to tell on the F-theory tensor branch. But I think for conformal matter and we could, like with the induced flow approach, we could identify all of them. But otherwise, we just miss one case, and we just like completely miss one case. And also for conformal, we need to be a bit more experimental. Yeah, I saw Craig has a question.
So nice that you raised your hand for this.
Yeah, of course, every time.
Yeah,
How,
good student.
Can you go? Lorenzo's also here. Can you go back to the E6 Hasse diagram that you drew?
Right.
One of the slices was confusing me.
Yeah, so we checked that this matches the one you had.
So what puzzles me is on the first diagram on the left, there's a slice that you label G2. So if I look at this looks like it comes from oh no, it is G2, no? I am right. It comes from this comes from 1 to SU2, right?
Right. So let me try to.
So why is that a G2 instead of an SO7?
Yeah, I wasn't prepared to. Let's see. So the first E6 kills E string, and the second.
If anything, we would expect G2 A1M, right? MA1 or B3 A1. This is what you're talking about, Craig, right?
Yes, I think
I agree.
A1.
Yeah, maybe it's a typo. Yeah, thank you.
Okay. I was just curious if I was missing something in the picture, but I think it should be a B3.
Yeah, thank you for pointing out.
We could also just add dimensions if someone can add
Yeah.
numbers in their head.
7
Speak for yourself. I don't know if I can.
I'm not gonna do that now. I won't do it.
Yeah. Okay, thanks.
All right. Thank you.
Thank you.
Not everyone has to raise their hand. It's also okay if you just.
Craig has set the example, so I feel obligated now. So you were mentioning plateau Higgsings. Can you do it also for exceptional? So going from E88 conformal matter to E7? Do you know what the operator is you need to Higgs there?
So there, those Higgsings would inevitably involve blowdown of -1 curves. So in some sense, I would count it as the combo Higgsing. And
Oh, so you would call that a combo. Okay.
right. So for D-type, there is the plateau Higgsing. So there's SO and SP, and you can simultaneously decrease them.
Mhm.
Yeah,
Okay. Okay. Thanks.
thanks.
Do we have more questions? Okay, so then I would say let's thank Hao again,
Okay. Thanks
and
again.
we can go off the record.